Okay, let's get started. So this is probably a third talk, at least at the minimum, on really focusing on light transport. So um, on the first day in the introductory lecture, I introduced the concept of the types of models one uses to simulate light transport in biological systems really depends on the spatial scale that you're considering and the sorts of light matter interactions that you really need to model, going from the wave, Maxwell's equation domain through to using Monte Carlo and the potential ability to use approximate solutions to the radiative transport equation when you're dealing with light transport over macroscopic domains. I also introduced this concept of a slightly different consideration one may have when considering light transport for, say, therapeutic or fluorescence applications versus diagnostic applications. And the former is really critical for you to understand the light fields on the interior of the tissue volume. Whereas in diagnostic and imaging applications, for the most part, you're really confined to visualizing the light field on the boundaries. And then you got the opportunity 2 days ago to actually do some very simplistic Monte Carlo simulations. And part of that was to start to build your intuition about both the spatial and angular distributions of light fields on the interior. You're able to look at light propagating down in the bottom hemisphere versus up and how that evolves as multiple scattering accumulates. And you also got to visualize light fields that are measured at boundaries. And that will not be your last experience doing that. We will have additional labs where you're gonna explore that a little bit more. So today I'm focusing more on how one can model volumetric distributions of light in tissues and focus more on, once we have the radiative transport equation, how we might simplify that equation to actually develop analytic solutions that are approximate solutions, but are nonetheless very useful, very critical to the early days of the field of biomedical optics, and are still used in many domains of diffuse optics. So my teaching objectives are, number one, we'll talk about this transition from the transport to diffuse regime and really focus on the diffuse regime today. And I'll focus on the derivation of the standard diffusion and approximation and a variant that Willem Starr in the Netherlands and Scott Prahl in his thesis developed, and that I also contributed to a little later on, the delta P1 approximation, which is a slight variant to the standard diffusion approximation, but actually provides much better approximate solutions. And so we'll talk about how these approximations are formulated from the radiative transport equation and what the underlying assumptions and limitations are. And then once we go through that and understand how those mathematical ideas are formulated, we'll talk about boundary conditions, because once you have equations to solve, differential equations to solve, you need boundary conditions. And we talked a little bit about that during Monte Carlo Day, about how one simulates or handles boundary conditions in Monte Carlo simulation, but we'll talk about how we handle those within the diffusion approximation. And then given that, I'll start to try to develop some intuition for you guys. Like I said, the focus today will, in my lecture, will be mostly on the volumetric distribution of light within tissue volumes, and then we're going to transition to things on the boundary in the next talk. But we'll talk about how the configuration of your source can influence the optical penetration depth of light in turbid tissues, and look at the impact of refractive index. You can be in an index matched situation, or you can be in a mismatched situation, how that, as well as optical properties, will affect the light transport within the tissue. We'll look at the impact of beam diameter and how that impacts the internal fluence rate distribution. And then I'll just very briefly introduce radiative transport in slabs, not in semi-infinite tissues, but in slabs, because that's actually quite critical to determine optical properties of tissue samples. And that's going to be the theme of the second talk from Scott. Okay. So these are the objectives, and we'll revisit these at the end of the lecture to make sure that you feel comfortable with these or at the end. Okay, so we're going to start with the RTE. This was introduced on day 1 as well as day 3 with Monte Carlo. Hopefully, while we haven't presented a rigorous derivation, hopefully you're somewhat comfortable with the conceptual idea of what each term represents. Okay, and so we have the time rate of change of light traveling in one direction at a given location is the sources of change are loss out of that location due to propagation along the direction that you're considering, omega. You can lose light at that location due to absorption or scattering at that location. And then you can gain light from light that has been propagating in other directions, but gets scattered at that location into the direction you're interested in. And the amount of light you're going to get scattered in is linked to both the local scattering coefficient and the probability of the scatter, the nature of the scatterers, which dictate the probability that you are indeed going to scatter from that arbitrary angle, omega prime, into the angle omega that you're considering. And then, of course, you can have sources. Okay. So, and then the key optical coefficients and parameters here are the transport coefficient, which is just the sum of the single scattering coefficient and the absorption coefficient, the phase function, which governs that probability density function, and of course, whatever volumetric source. So as we've emphasized, the main variable that we're solving for is the radiance, which is a function of space, angle, and time. And this is a challenging equation to solve analytically. There are analytic solutions for propagation in a slab with a uniform beam. And that's actually, the solution to that equation is actually used to validate Monte Carlo simulations. So like our Monte Carlo solver, whenever we make changes, we make the Monte Carlo solve that 1D problem and make sure we're still getting accurate solutions. So there are various ways to validate Monte Carlo, and we make sure that at every step, we are generating solutions that are transport rigorous. And that's a very important step that not all, I think, Monte Carlo's engines that are out there actually take care to do. So let me go into the diffusion approximation. This is really a very important kind of formulation at the early stages of the field, back to the 1980s, probably before all of you were born. So I'm going to restate the radiator transport equation. You're familiar with it now. I moved the directional derivative or the flow out of that volume to the other side. And what is done in the diffusion approximation, we say, well, this we're modeling light propagation out of a point on the unit sphere. That angular distribution can be very, very complicated. But the concept is that if light undergoes enough scattering and loses its memory of its initial propagation direction, at a certain point, basically, you're going to have light that's basically uniform. It's traveling in all different directions. But then if you kind of zoom back, you can imagine regions where there's more light and regions that there's less light. So there's a bias. There's a flow of light from regions where there's a lot of light to regions where there's less light. So an easy way to do this, so there are these family of polynomials called Legendre polynomials, which form an orthonormal basis on the unit sphere. There is azimuthal symmetry, so you don't consider variations in phi or variations like around the Earth, but you consider variations in latitude. And that is the cosine of the polar angle. So what we say is this, is that let's just approximate that angular distribution by having one term, which is the average amount of light emanating from that point on a unit sphere. So you have something that's not a function of omega, it's just constant, okay? The same amount of light emanating everywhere. And then we also have light that we know that there are regions where there's a lot of light and less light, and so we have to have a net flow of light. So the first Legendre polynomial, that's function of theta, is just a cosine, right? So you have, if you're going in theta equals 0, you have cosine is 1. pi over 2, 90 degrees or 270 degrees, you have nothing. And then if you go backwards, you have less. And so what we do is that we superimpose onto this uniform distribution a cosine theta variation. And that gives you this net flow. And so diagrammatically, this first term is isotropic. You have, from that point, you're emitting equally in all directions. And then there's going to be a region, say, where there's lots of light to a region where there's less light. And so we superimpose on that a cosine theta variation, which would look like this, right? In the forward direction, you're going to have a little bit more light. In the backward direction, you're going to subtract off some light. And so this will generate a angular distribution where you have more light moving in one direction and less light moving in the backward direction. And there's really not much change relative to the uniform distribution at 90 and 270. Okay? And so this net bias is called, in our field, so this is probably known to most of you as fluence, phi. That's the isotropic or uniform component. And then the net bias is called the flux. So it indicates a light flux. Those of you who may be familiar with heat transfer, you think of heat flux, for instance, the directional transport of heat. It is a little confusing in the literature. Hold on, I should go back. Actually, and then you do the same thing with the single scattering phase function. Now, the probability distribution of light scattering can be also incredibly complicated. We visualize that using the Mie scattering thing, but we do something very simple, and we do the exact same thing. We just say that this angular scattering function is uniform plus a cosine theta. Okay, and the 3 just comes out of the normalization of the Legendre polynomial. So that's just necessary to form the orthonormal basis. So, and then G, you see the single scattering anisotropy, the mean cosine of that, of the phase function is G. So that it appears explicitly in that phase function. I have a subscript E that represents, stands for Eddington, Sir Arthur Eddington, who was a cosmologist, astrophysicist, looked again at light transport in the atmosphere, and was the first person to come up with that phase function. So what we do is that we take these very simplistic analytic forms for the radiance and the phase function, and we put it back into that equation. And what we do is that we just say, okay, we have the isotropic term, we put it into that equation, and you can get a differential equation, and then you put in the cosine term into that equation, and you get another equation. And I will spare you the details of that. And you get these two coupled ordinary differential equations. Okay, so the first thing I want to mention is that, remember, phi is a scalar, right? So it varies as a function of space, but it's uniform in all directions. J is a vector, right? Because it indicates the direction of flow, right? And so the orientation of J can vary just depending on your configuration of sources, and it's not uniform in the material, right? It depends on location. And so you get these two coupled differential equations. The interesting thing here is J is proportional to the spatial gradient of the fluence. That kind of makes sense, right? And a gradient tells you the direction in which a scalar field is increasing the most. And of course, light is going to travel from regions like heat will travel from regions of a lot of light to regions with less light. So we have the negative here. So that's why a lot of people call this the diffusion approximation, because you get this relationship of the net flow to the gradient of the fluence, very similar to how you have heat transfer, where your heat flux is the gradient of the temperature distribution, for those of you who may be familiar with heat transfer. And then you have two unknowns here. You have the fluence rate phi and the flux J. In some literature, it gets a little confusing. In our field, this is usually referred to as the fluence and the flux. In other literature, fluence is actually referred to as the flux, and they call this the current. So just if you are so inclined or so insane as I was, if you wanted to look at so much of the literature, you can get easily confused, because some literature they're referred to the flux and they're actually mean the fluence. Again, it's I think I can't remember what is the electrical engineers call it, flux and current, it's like one of these physicist chemist sort of thing. I don't know. Yeah, yeah. It's so okay. So yeah, and so you got all this stuff going on here. Okay, so then you can combine these and you can result in one partial differential equation that you end up with. And so this is the diffusion approximation in all its glory. You have a Laplacian in the fluence. Then you have a term that represents absorption loss. And then that equals two different time derivatives, one that gives you some sense of wave propagation, wave-like propagation of light, something that looks like a kind of a diffusive propagation of light with time, and then you have a source term. Okay? Yes?
It's intuitive reasoning for like the value of 3, like why is it?
There is not an intuitive reason. I think the whole issue is you probably back at some point understood or learned about developing like orthonormal functional bases, and that you have to do the integration. Number one, they have to be orthogonal to each other in function space. And secondly, if you want to do orthonormal bases, there has to be some conservation of the integral. And that the 3 arises through the conservation of the integral in the Legendre polynomials. If you go to the wiki page of Legendre polynomials, they will give you all of those details. But I think for the purposes of this lecture, let's not get into those weeds at this moment. So one thing I just want to point out about this equation, there are a number of features about this equation. So as you notice in the radiative transport equation, mu A and mu S appear separately, right? Here you have mu T, which is the linear sum of mu A and mu S. And of course, here mu S appears separately. In the diffusion approximation, it's very interesting what happens through this process. You get an optical coefficient here, which is mu A, and mu TR is the sum of mu A and mu S prime, okay? And then you similarly see here mu S prime and again mu TR, which is the sum of mu A and mu S prime. So mu S no longer appears as an independent variable. Wherever you see mu S, it's in the form of mu S prime. And then here mu TR is mu A plus mu S prime. So you lose sensitivities to the single scattering coefficient. And so basically for a given value of mu A, all pairs of mu S and G that produce the same value for mu S prime gives you the same solution. So you lose sensitivity to the details of the angular distribution. The other thing you see is that, again, how many of you guys have taken like heat transfer or mass transfer, like diffusion processes before? Let's go. Okay, so this kind of looks like a heat transfer equation. If you remove this term and this term, you basically have an equation that looks very much like a heat flow equation. The two changes that happen in light transport is number one, you have loss because you can lose light. Unlike heat, you have to conserve energy everywhere. You can't make heat disappear. You can make light disappear through an absorption. And the other thing is that you get a wave-like propagation, although the velocity of the propagation is wrong. So those of you who may remember wave equations, the term in front of this second derivative, if you take the square root of this and make a reciprocal, that should be the speed of propagation. Well, if you do that here, you get a speed of propagation of the velocity of light divided by the square root of 3. So the speed of this diffusive wave is actually slower than the speed of light, which really violates, obviously, the speed of light. So you can see that at early times, you're going to have problems. The solution to this equation is not going to quite work. The other thing is that often in the field, people just ignore this term because you can show that this term is small compared to that term. But if you keep it in, you do something, it's called the P1 approximation. You're taking the full, the contributions of both this isotropic and anisotropic term. If you get rid of it, That's what's called the diffusion approximation. And you can get under circumstances where mu s prime is much larger than mu a, that's reasonable. But if only mu s is much larger than mu sub a, you probably want to keep that term in if you're dealing with a time varying problem. Okay. So any questions? I know the math is heavy, but again, I'm trying to focus more on the physics rather than the details of the math. Yes, Vrinda.
US prime, using US prime versus just US.
So it comes out of the math, essentially, but essentially you lose when you put in these approximations into the main equation, you see that wherever mu s appears, it appears multiplied by 1 minus g. And so, and that essentially means that the diffusion approximation will not allow you to examine how the light field will change if only g changes, but not mu s. So you lose that independence. And conceptually, that makes sense. What it tells you is that where this solution lies in the domain where you've had so many scattering events that you're no longer sensitive to the angular distribution of a single scattering event. Because that's what G, in some sense, gives you a notion of, is how angularly oriented is a single scattering event. But because we're implicitly assuming a very gentle angular variation in the light field, you're no longer sensitive to the details of a single scattering event. Does that help answer your question slightly? Yeah, okay. You lose the angular information. I mean, you only allow the angular information to be expressed in terms of a cosine. You don't get any additional details. And G represents the mean cosine. So you don't get any additional information of scattering beyond this grouping of mu s with 1 minus g. So you do capture the mean cosine elements of, I mean, obviously this term represents the angular variation, but only simplified. The most sophisticated way you can show that is in a cosine functionality, which is very gently varying with angle. So you can see right away is that, and you experience this in your Monte Carlo lab, very close to the source, there's a lot of light coming in one direction, very little coming out. A cosine functionality is not going to give you sufficient accuracy to do that. And those are precisely regions where diffusion approximation doesn't do that. Okay. So you really need to get away. You got to be in regions where light has scattered enough so that, you know, the angular variation is much more gentle. Okay. Other questions? Yes, Anna. Yeah, watts per meter squared. That's right. Yeah. Yeah, 4 pi. This is the radiance approximation. So yes, this is to get the 4 pi steradian. Yeah. That's right. And this is the steradian. Yeah, that's right. Correct. Other questions? Okay, so let me go to the next. So some helpful solutions. So you can solve that equation in spherical coordinates or planar coordinates. Again, I'm not showing the derivation for these, but in spherical geometry, if you just have a point source, this equation gives you both the spatial and temporal distribution of a impulse in a spherical geometry. This gives you the solution. If you integrate this over all time, you get a steady state. What's interesting about this is that this gives you the spatial attenuation coefficient. And I guess I should go back to this. People may remember if you just solve the left-hand side and you have 0 on the right-hand side, the solution will be exponentials in the square root of this coefficient. And that is called mu effective. And those of you who are in tissue optics probably hear a lot about 1 over mu effective representing a penetration depth of light. It's kind of, people use that as a proxy for approximating, you know, how deep in the tissue will light propagate. It has limitations, as I will show. Something that annoyed me and Scott to no end when I was a graduate student, because it's very limited in its accuracy and deeply flawed in some way as a metric for penetration depth. And we'll talk about that shortly. And then you can look at another, so this is kind of 1D in spherical geometry where the only spatial coordinate is R. This is 1D in a planar geometry. We have similar things here, and you can see again this spatial variation in mu effective. Which circle? It's not a circle. It's not meant to be a circle. This is an infinite medium, a blob that, yeah, extending out to space. Sorry. Yeah, maybe I should do to infinity. Yes. Yeah, I didn't want to pretend this was like yeah, got it. Okay. So as I just said, or implied, in our field, we often use highly directional sources. The other thing I should mention, maybe in passing, make you realize is that this represents cosine theta. You can imagine that for g values much larger than 0.33, this term makes the entire phase function negative, which kind of makes it, because cosine is at the reverse direction is -1. If g is like 0.4, this is going to be negative, which is completely nonsensical. This is a probability density function. How can you have negative probabilities unless you're dealing with quantum phenomenon where there are negative probabilities? But anyways, so clearly this has some limitations in accurately modeling media which have high values of G. And guess what? That's tissue, right? Tissue has, G of 0.8, G of 0.9 is very common, right? So is there any way we can improve this in some way? And this is, like I said, this is an idea that first was brought into tissue optics by Willem Starr, and Scott did a lot of work. Major chapter in his thesis was on using the concepts that I'm going to introduce here. So we have the same radiative transport equation, and the idea is that, well, when you're very close to the source, you're going to have a large component of the light that is strongly influenced by the initial direction of propagation of the light, right? Sometimes you're just shooting a laser directly in. And that's a collimated component of your light field. And it transitions into a diffuse component after it undergoes scattering. So we thought, well, why don't we subdivide this entire radiant field into a diffuse component, a scattered component, and add explicitly in a collimated component, which only resides along the direction in which the light is injected. Okay? And so we denote the initial direction in which the light is injected as omega naught. And in the same way, we do that for the phase function. So I now call this, instead of the Eddington phase function, this is the delta P1 phase function. And we say, well, let's keep a fraction of the light before it is scattered, collimated, okay? And the 2 is here is because the collimation is happening only in one direction, or like in one hemisphere. So you have to make the normalization work out, you need a factor of 2. But F is the fraction of light that remains collimated along this direction, omega naught. And the rest of the light, 1 minus F, scatters again as a cosine. But since you've taken some of the light and maintained collimated, the G here is a little different. Is a G star, and this G star will always be less than G, okay? Because I've taken some of the angular variation in the collimation away. And so that helps with the cosine element, because you've taken a component of the light which is strongly forward directed away and put it in collimation. And if you do that, again, I'll spare you the math, you get the exact same equation for the diffuse light, but the optical coefficients are slightly altered. So this is the radiative transport equation again. Instead of mu t here, you get mu t star, which is mu a plus mu s star, which ends up being mu s times the quantity of 1 minus the second moment of the phase function. And you get a modified g value, which is essentially the first moment of the phase function divided by 1 plus g1. Again, I don't want to bother you with the minutia, but the emphasis here is that the RTE with the delta P1 phase function has the exact same form as the RTE in the standard diffusion equation, but you're using just slightly altered optical coefficients. And as you'll see, this very small change leads to a dramatic improvement in the accuracy of your predictions. So, so then you can actually then, do the same thing, shove these, the radiance approximation and the phase function approximation into RTE, do those two coupled equations, get a ordinary differential equation. And again, the equation is actually essentially identical, except the source is just slightly altered. Okay? And this is all laid out in all its gory details in that paper. I think that's the only paper that we wrote together, Scott. Yeah.
We barely talked to each other.
If I remember, I think we wrote down the outline to that paper 10 years before we actually got the paper out. So it was fun times. Anyways, good. So let's talk about boundary conditions. Oh, maybe I should pause for any questions and I can make you even more confused. Any questions on this? Again, I just want to emphasize the concept. Does it make intuitive sense that if we strip away some of the light in the collimated component, it makes the cosine theta approximation a little bit better, right? Because I'm basically taking the most difficult part of light to model because it's so forward direction. And let's put it in this box, and then let's just deal with the stuff that remains, where this gentle variation should be better modeled. And then we just add it back in at the end.
You're removing a column light that's like.
I just kept it here, yeah.
It's like forward.
Yeah, it's actually only in the direction of your collimated beam.
Okay.
Yeah.
Well, all the other ones that look.
All the other stuff is diffused.
Slightly varied.
Right, so close to the source, you're going to have a significant amount of the light that's collimated. And there's actually very little diffuse component right close to the source. But as you go deeper and deeper, this goes to zero and everything becomes diffuse eventually after everything scatters. So the ratio or the relative magnitude of these two terms change in space, okay? And so instead of making everything diffuse from the get-go, you're allowing in those regions where you have a collimated light field to put some of it in this box. Yeah. Yeah. Yeah.
For some of the first ones, like there was like basically no photons, like just near.
Yeah.
Is that because of this information or is it?
Yeah, in some sense, yeah. I mean, Monte Carlo, you see it in gory detail because the minute you have a single scattering event, it gets kicked out of that center. Part of it is an artifact because we're doing that in cylindrical geometry, and the center bin has the smallest surface area. So the moment you get scattered, you're going to get kicked out of that central bin. But if you have a bin that has a little bit more finite spatial extent and finite angular extent, I mean, you have lots of light in that center line. It's just kind of an artifact of that aspect of the simulation. Yes, Eugene. Say that, I'm sorry, I caught the beginning of your question.
So the fraction.
Yes.
We're determining how much of that we're assuming is collimated or calling it collimated.
Yeah, it stays
So
collimated,
how
yeah.
do we determine the fraction? Is that just like over to us being all of these situations?
No, the fraction is actually, the fraction of the phase function actually ends up being determined by the mathematics. Because again, this has to be a normalized probability density function. And we basically have to maintain the conservation of that probability density function while satisfying the demands of the Legendre polynomial at the same time. And so you end up having two equations and two unknowns, and there's a relationship between f and G star and the original phase function, which is just without this n1 plus 3G. And so F is explicitly determined. It's actually 1 minus the second moment of the phase function. So there's no guesswork. F is explicitly determined. Yeah. And so the higher that and for the Henry-Greenstein phase function, the second moment is G squared. Okay. So that's one of the nice yes, Henry-Greenstein made it up, but they made it up so that if you know the first moment, you know all the other moments. So in the Henry-Greenstein phase function, the first moment is G, second moment is G squared, third moment is G cubed, yeah, and so on. That's not true for all phase functions, but it's explicitly specified here. Okay, so you can, if you've solved the standard diffusion approximation, you've solved delta P1. You just use slightly different coefficients. Okay, so let's talk about boundary conditions in the standard diffusion approximation. I think most of you all know from your high school physics that we have that Snell's law provides this relationship between incident angles and refractive angles, and what's very important in terms of both diagnostics and therapeutics is that we need to handle the fact that you can have a light source. I've just expanded the spatial scale. Just imagine this light source being very, very close to the surface. That close to this boundary, you're going to have a fraction of the light that gets transmitted back outside, say into an air environment, and some of the light that gets totally internally reflected. And so that creates challenges, both in Monte Carlo as well as in the diffusion approximation. This gives you a diagram for how the reflection and transmission varies as a function of the angle of incidence. So in reality, most of the light for a 1.4 refractor index mismatch gets transmitted at the boundary. When you get very close to this critical angle, it goes very rapidly to 0. But it means that you have to be within that critical angle, which is about 45 degrees, for the light to escape. If it's beyond 45 degrees, it's going to get totally internally reflected. So in some sense, for getting accurate predictions for reflectance and transmission, what's important is actually not necessarily accurately determining the light field in the whole hemisphere here, but you actually only need to really predict it well for the, for plus or minus 45 degrees, because the other part of the distribution doesn't have any impact on the transmitted light, but it does have an impact on the internal light field. So the question is, how do we handle this? And actually, our colleague Tin, I think, asked a question about this to either Scott or Carol. I can't remember. How do you handle this? Talked about photon splitting a little bit. So I'm going to just unpack that. You have this choice in Monte Carlo of how you handle this, right? You can say, well, this photon is the next step size, asks it to cross this boundary. Do I have to split the photon? And you can. You can split the photon and say, well, the fraction that gets reflected, we're going to let propagate in the medium, and the fraction that gets transmitted will tally on the outside. Or you can do what is often done, and what we do in our Monte Carlo is that you run what's called a roulette. You say, let me take a random number between 0 and 1. If it ends up falling between 0 and the reflectance, we let it propagate inside the media. If it falls between the reflectance and 1, we let it go out. Okay? And if you propagate enough photons, and you have enough photons hitting the boundary, you will converge to the same answer. Okay? This will probably converge faster, but at the expense of more computational cost. So because you've got to deal with the tracking. So how do we deal with this in the diffusion approximation, right? We're not doing individual counting of photons. How do we deal with this? And so what we have to do is this. So this is the equation, how you formulate this in in the diffusion approximation. So this is an integral where the dot product between the inward pointing normal and the angle of the light is greater than 0. So this represents all of the light that is going down in the medium. So this is all the downward propagating light at z equals 0, but just inside the medium. So what we say is that all of the light that is flowing down from this interface has to equal the light that was going up. So this is z dot omega less than 0. That means that's the light that's going in the upward hemisphere. The light that's going up from that domain, but gets reflected back in. And that's given by the Fresnel reflectance equation, which I have on the previous slide. Okay? Because there's no, I mean, this is in the absence of external sources. You can add the source back in if you have a source. But basically, the light coming down from this boundary has to emanate from light that was formerly traveling up, but gets totally internally reflected. Okay? And then you do the same thing. You say, hey, I have the radiance approximation, which is the isotropic plus the flux term. And then you shove it into those equations, and you end up getting this equation, which is known in PDE's theory as a mixed Robin condition, because it's connected to both the fluence rate as well as the derivative of the fluence rate. And these are the first and second moments of the Fresnel reflectance equation. And there are tables that you can find. You can calculate it, but there are also tables in the literature to give you the values for different refractive index mismatch. Yeah. Any questions there? I've saved you. I mean, if you want the references and you want to look at the derivations, I'm happy to give them to you. But I think, again, it's the physics of how we deal with it that's of prime importance here. Okay. Okay. So just let's think about this, because often we're interested in reflectance. Again, I want to emphasize that these refractive index mismatches introduce discontinuities in both the magnitude and angular distribution of the radiance. So, in some sense, it's a small angular interval of light that when it crosses the boundary, when you're going from a high refractive index to low refractive index, this smaller angular area of light gets expanded or spread out to a larger angular area, right? And so if you're looking at the radiance field here, I want to make sure I have the, no, okay, so I don't have that. You end up getting a discontinuity in the amount of light on this side of the boundary and that side of the boundary. And then the total internal, let's see, what am I trying to say here? I'm trying to figure out what this is, which I don't quite recall what I was trying to do there. Anyways, so if we want to understand what the radiant field is on the other side of this boundary, you calculate what's on the interior of the tissue, and you multiply it by the refractive index. And you actually transform both the amplitude of that field as well as the angle of that field, right? Because obviously the angle on the outside is different than the angle on the interior. And then if you just want to do reflectance, you just integrate over the backward hemisphere of the radiant field on the other side of this boundary.
I think it's hard to see, but you have the
Yeah, I haven't shown. So this in the second cone. Oh yeah, I do have. That's right. I do have a hemisphere. Thank you. You're right. That's why I was saying that graphic didn't quite. Yeah. So what I'm trying to say here is that if you take, thank you, if you take this theta all the way out to the critical angle, it's a smaller angular interval that gives rise to the entire hemisphere of light coming out on the other side. Thank you. Yeah, so that doesn't quite look right. And what was I trying to do there? Yes, that's exactly it. Okay, thank you, Brian. Good. So now let's get out of the math and try to start to develop some intuition. So one vexing gripe that me and Scott had was number one, that the standard diffusion approximation didn't do a very good job in predicting the internal light fields of collimated sources close to the source. Get horrible errors. And secondly, because of that, in part, the literature was rife to say, oh, if you want to approximate the penetration depth of light in the material, just do 1 over mu effective. It's going to give you a great which is abjectly wrong. And so those are kind of our two, we would gripe probably over lunch like 2 to 3 times a week about that. And, yeah, that's right. So we wanted to first do modeling of some simple irradiation geometries and come up with kind of more, valuable metrics for light propagation. So for what I'm about to show, I'm considering 3 different types of sources. One is kind of the classic, very small beam incident on to material, and you may be interested in looking at what is the light field right under that source as a function of depth. And then in terms of approximating penetration depth, you can imagine 2 situations. One is that, you may just want to know at what depth do you exceed some sort of minimal fluence rate that you want to achieve in the material. And that could be maybe just linked to the incident light that you have. So, what is the 1 over E depth of that light? And we call that, for lack of a better term, pi for penetration P. So we just want, at what depth do we get a certain intensity? But then there are other situations where you're actually more interested in the amount of light that's absorbed. So say that you want to create a temperature rise, or you want to make sure that a photochemical compound gets activated and you need a minimum amount of light. And you want to know where is most of that light absorbed. Well, there we want to just integrate the radiant field, and we want to say where is basically 2/3, or 1 minus 1 over E of the light, where is it absorbed? And we call that capital delta for dose, right? This is the dose of light, and how far can we dose the light effectively? And so you need accurate predictions for this radiant distribution. You can look at it for a pencil beam, Gaussian beam, planar beam. So let me just, and so the other thing that I wanted to mention is that I'll get to that in just a second. So again, the governing equation is 1 over mu effective. In standard diffusion approximation, the laser radiation usually is attenuated by minus mu TR with Z, which is mu A plus mu S prime. So basically, the loss of your collimated light is either due to absorption or due to an isotropic scattering event. And the power of that light is linked to the reduced scattering and the transport coefficient. But there are changes that are made in the delta P1 approximation that makes it more effective in terms of the mathematical formulation of that distributed source. And that's linked again to the equations I showed earlier. So now let's look at some distributions. So this is the dots here are Monte Carlo simulations, and I'm going to show results first with Monte Carlo simulations, show you how the standard diffusion approximation does, and then show you how the delta P1 does. So here we're looking at a planar wave. So maybe I should go back to so the first set of results, we're going to just consider this situation where you have a beam that's infinitely broad, incident on a semi-infinite medium. And these Monte Carlo simulations show you what is the spatial decay of that light field as a function of depth. I've normalized the depth relative to what's called the transport mean free path, which is 1 divided by the sum of mu A plus mu S prime. Okay, so that's very common in our field. And then I looked at media of various relative amounts of scattering to absorption. So the red dots here are very, very highly scattering media where reduced scattering exceeds absorption by a factor of 100, and then more moderately scattering 10, 3, and then fairly highly absorbing down to 1. And then here I'm looking at a refractive index matched situation where you have index matching. So you at the surface, okay? So one question I have is so this, you can imagine this is, I know maybe not realistic. This is what happens. This is the internal light field where, say, you're shining a laser beam onto a piece of tissue that is submerged in water. Okay, that, so you would allow the light to escape from the tissue if it reaches the boundary. So if I take that piece of tissue and put it in air instead, what is your intuition on how these light fields will change? Any thoughts? Some people say that shouldn't change at all. So nobody says, okay, so you all know that it should change. How do you think it might change? Or what do you think, what is different between the tissue being in water as opposed to air in terms of the light transport? What have I changed implicitly?
Is it easier or harder for the light to escape?
If you're in air as opposed to in water? It's easier in air or easier in water? In air? Why do you say that? Right, right. So if you're in water, you have tissue in water, the light comes up to that boundary, and what is the mismatch, refractive index mismatch across that boundary? It's basically nothing, right? That means no matter what angle that photon travels towards that boundary, it's going to be able to escape. But in air, there's some light that can escape, but the light that's beyond the critical angle gets trapped, gets back in. So what that ends up doing is that it traps more light in the tissue, and therefore pretty much all of these curves will go up. And that's what you see. Yes.
What I'm talking about is we think that a tissue has refractive index roughly of 1. I know it's
No. Oh, yeah. Or I should say that there's no mismatch between, right.
Yeah, on the graph I know it says n equal 1.0.
You're right.
It's basically water.
You're right.
Put it in the air.
Right. Or really, I was meaning this is the relative refractive index between the tissue and the outside medium. Yeah, but that's an important clarification. Yeah, so that may have confused people. So what I mean by n equals 1 is that the relative refractive index between the tissue and the surrounding medium. Okay, thank you, Tin, for that important clarification. Maybe that helps. So when you have a refractive index mismatch where the tissue is higher than the surrounding medium, you have, for the light that's traveling back towards the boundary, some of the light can come out, but not all of it. Some of it gets trapped. And so that actually promotes the trapping of light, but the impact of that is much more important for highly scattering medium than a highly absorbing medium. You can see for one, it doesn't really change it at all. And why do you think that's the case? Why do you think that you're seeing this elevation only for the highly scattering medium, but the impact of that gets reduced as the medium becomes more absorbing?
I think it's like so many of the photons are absorbed that scattering, like it doesn't really change.
That's right. I mean, how much light is going to be reflected in a highly absorbing medium? There's just not that many photons that are traveling back up. There's some, and so you see a slight change here, but it's not going to propagate down here. So good. Good. Okay. And then it's nice to, so this is what the standard diffusion approximation predicts for these situations. The solid curves being for the refractive index matched and the dotted line for refractive index mismatch. So you see a couple things. In the highly scattering situation, it does pretty good out here. But you start to see that, say, maybe, and this is log scale, so it actually, is quite kind. I mean, once those dots are coming off of the curve, you're actually incurring a fair bit of error. Even out here, you're like 10, 20% off. See, even down to 3 transport mean free paths, if you're more superficial than that, you're really incurring a fair bit of error. And it starts to get worse as the absorption of the medium increases. So the other thing you see is that the depth decay is fairly good, not great, not perfect, but fairly good with depth. But here you can see that the slope of the diffusion approximation with depth is not really the same as the Monte Carlo. So as you get more highly absorbing, even the far field attenuation is actually incorrectly modeled with standard diffusion. Okay. If you go to delta P1, it's quite good. And it's quite good even for the highly absorbing cases, because what happens is that in highly absorbing media, the light stays collimated for long periods of time, and we can handle that collimation through the introduction of the collimation term. And because we're able to better handle strongly anisotropic light fields, we do even better close to the surface as well. And so what, Scott, you're saying when you're first doing standard diffusion approximation, you would get negative reflectances with SDA, but once you put in the delta P1, you actually get reasonable estimates for reflectance. So this small change, I mean, the equation is no more complicated. You're just using slightly different optical coefficients. You can get actually a very dramatic improvement in your predictions. Okay. 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 So now let's look at these penetration and dose steps. So what we did here, again, me and Scott drank too much of the dimensionless and non-dimensional metric Kool-Aid. So we did everything in dimensionless coordinates. So this is not a physical depth, but it is the physical depth times mu effective. And mu effective is an optical coefficient, and it's an inverse length. So this has no dimensions. But what it allows you to do is that if you use this chart and you multiply it by the mu effective, you apply the number multiplied by mu effective, you get the physical depth back. Okay? So this chart works for tissues of whatever mu effective it has. And then on the bottom, we're showing what mu s prime or mu a is. So first you calculate what is the mu s prime or mu a of your medium. That dictates to you where along this curve you should look. And then you just go up and find the symbol you're interested in, and then you read off the dimensionless depth, and then you multiply mu effective, you get the physical depth. This is the penetration depth, pi, right? This is where in your tissue the fluence rate falls to 1 over E of the initial fluence rate. So that's really kind of the classic penetration depth. And this is delta, the dose depth. This is the depth at which basically 2/3 of the light gets absorbed. Okay. These are all Monte Carlo simulations. Okay. And you see that the penetration depth, again, as you would kind of intuitively guess, for the refractive index mismatch situation, it goes deeper, right? Because you're trapping more of the light because the light can't escape from the surface. It penetrates deeper, so that makes sense. It doesn't have that much impact actually on the dose depth as much. So that's what you get here. What's interesting here is you can see that all these curves converge to a value that ends up being the square root of 3 for the case of perfect absorption. And that's because mu effective is the square root of 3 of mu a times mu s prime. Here mu s prime is 0, so you know that the penetration depth for a highly absorbing medium is 1 over mu a, right, given by Beer's law. But of course, and you get square root of 3 because mu effective in the case of no scattering is the square root of 3 mu sub a. So you need to get the square root of 3 out of there. Okay, standard diffusion approximation has some problems. You can see with the dose depth, it actually really doesn't give you good predictions anywhere, maybe at one point. But it's garbage, essentially. Sorry for my frankness. But it does, a reasonable job for above ratios of scattering to absorption of 10 for a refractive index matched situation, not as good for the refractive index mismatched situation, which is quite surprising, right? Because that's probably should be the domain where it works well. And the other thing is that you would, the literature would say your penetration depth is mu effective, which is down here. So, right, if you just follow the literature, oh, I need to estimate the optical penetration depth, well, I'll say what's mu effective. So the literature tells you this is the penetration depth. So in fact, you penetrate a lot more than mu effective, as indicated by the Monte Carlo simulations, right, which is kind of gold standard, okay? And there's a significant variation with optical properties. And then the magic of delta P1 is that that's what delta P1 gives you. Yeah, and so we're very happy with that result. And again, there's no added complexity mathematically between implementing delta P1 and the standard diffusion approximation. I have a lot of charts here. You have the slides. I'm trying to figure out. I have about 15 minutes. I think it may be more worthwhile to kind of skim through these. You have them. So this, we illustrate how the fluence rate varies as a function of depth for beams of different sizes, because what I showed to you is a very idealistic case of a plane wave incident on a medium, but in reality, we use finite beams. And so you can see that as your beam size gets smaller relative to L star, your penetration depth, of course, goes down. Makes sense. This is for a highly scattering case. This here, I only showed the delta P1 results. The standard diffusion approximation gets even worse than what you saw in the plane wave approximations. This is what they look like for lower scattering media, where mu primary media is only equal to 1. I show optical penetration depth for Gaussian beams, right, which is often used. These are penetration depths as well as dose depths. Again, the delta P1 does fairly well. It starts to break down as the beams get small. And you see that here for the dose depths. So you can look through those if you're interested in these sorts of curves. But there are often times in the lab that you need kind of a back of the envelope approximation, and these curves are really important, really helpful. And then, just as a segue to transition into Scott's talk, everything I've shown you is in semi-infinite media, and light transport in slabs is a very important problem because you can actually get very good results using delta P1 in slabs of modest thickness. But the key thing here is that internal distribution results in your measured reflectance and transmittance. And in slabs, in a case where slabs are thin, you don't necessarily establish a diffuse light field on either side. And therefore, the reflectance and transmittance is explicitly a function of mu A, mu S, G, and D, where D is the thickness of the slab. And these unique relationships between the optical properties, G, and the slab thickness allow you potentially to get accurate measures of the optical properties if those measurements are done well, which is far from trivial. So to summarize, standard diffusion and delta P1 approximations use analytic representations for both the radiance and phase functions, right? That analytic representation is in terms of angle. So we represent the radiance as a sum of a uniform distribution plus a cosine theta variation to handle the directionality. Monte Carlo transport solvers handle the boundary conditions explicitly because they deal with things on a photon by photon basis, and they deal with that reflectance and transmission on a detailed basis. All you can do in the standard diffusion approximation, or delta P1, is to conserve that interaction on hemispheres, right? I say that the light coming down from that boundary has to equal the amount of all the light that goes up over the entire hemisphere multiplied by the fraction that gets scattered down, right? So we can't do a detailed balance. All we can do is do hemispheric integrals. Um, and then increases in refractive index, meaning mismatch, meaning if you have tissue and air as opposed to tissue and water. Refractive index mismatches enhance total internal reflection. It increases the amount of light that stays in the tissue, and it helps with optical penetration, but more so for the penetration depth as opposed to the dose depth. We saw that standard diffusion approximation isn't that great. Provides poor predictions for internal fluence rates and optical depth, certainly for values of μs prime or μa of less than 30. Delta P1 provides much improved predictions, but the predictions do tend to break down when the beam diameter gets small and when μa and μs prime become comparable. And finite beam diameters further reduce optical penetration depth, especially in higher scattering medium. In lower scattering medium, not so much because you don't have as much scattering and you basically have a beam that just propagates in a straight line. So it doesn't really matter. So last slide is just our teaching objectives. And so hopefully those have been accomplished. If they have not been, that's what Q&A is for. So thank you for your attention. Happy to take questions. Yeah, Yujin. Let's wait for the microphone, Yujin. Thank you. Thank you.
No, this is just really quick. For the beam sizes,
Yes.
what are the units for that you were showing for the beams? I don't know if I
Yeah,
missed it.
sure. No problem. So I forgot to number the slides this time. So
Yeah.
so here again, we drank the dimensionless Kool-Aid a little too
Oh,
much.
I see.
So this is the radius of the beam in units of L star.
Okay, so yeah.
Yeah.
Thank you.
No problem. Other questions? Too much math. Oh, okay. We got questions. Okay. Najib.
In the delta P1 approximation derivation,
Yes.
I was wondering, like, could you go back on the F and delta parameters?
Yes. Yes. So let me see how best to describe this. It's been a little while since I've looked through the details of this. So essentially in SDA, you I think it's best to look at the SDA first. So in the SDA, what happens is that you don't deal with collimation explicitly, and you have two components that you have to solve for, right? And therefore, you can only have two independent optical coefficients. So that's why in the general case, you have μa and μs prime, but G gets collapsed into the μs prime because you only have two independent coefficients. When you go to delta P1, you're introducing an additional component. You're introducing the collimation. So, and so what happens is that actually LD has two components and the collimation has one. So you have a total of three components. So, and so it's that additional component that you have that can allow you to define what F and G star is independently just based on the value of characteristics of your phase function. Because what you're doing is that you're decomposing your phase function into three components, right? Collimation plus the uniform and cosine theta. And based on that relationship and the need to enforce orthonormality of your phase function, you can determine what these values are. The paper, I think, is by Douglas and Weinman, I think. Douglas, yeah, I have the paper if you want to go through the derivation for how you get F and G star from the characteristics of the phase function. Yes. Exactly. Yeah. So I can give you Douglas something and Weinman. I have it on my computer. I just have to dig it out.
Right.
But I just wanted to save you from the gnarly mathematics. But it's all determined. Yeah. There are two other. Yeah. Brenda.
Can you give a real life lab example of when you would use diffusion versus standard, or the P1 versus standard diffusion versus Monte Carlo?
Okay, so number one, this only comes up when you're doing time resolved, right? Because the only thing that's different between P1 and SDA is the time varying term, right? So in the case, so let me just go back to the equation. So the only difference between diffusion and P1 is this term, and that's a time varying term, okay? So if you're doing steady state, P1 and standard diffusion is the same, okay? Because that term doesn't appear at all, right? It's time varying. When you use SDA, you have only a first derivative in time, which means that if you use SDA to solve reflectance as a function of time, you will get a non-zero reflectance immediately, like right after time equals 0, because the first derivative propagates things everywhere at infinite speed, okay? If you introduce this, you will see a finite time delay at early times, because this actually gives you a finite speed of propagation, okay? But it's still wrong. The speed of light will come out later than it should based on ballistic transport. So if you need finite propagation, albeit wrong, as opposed to infinite speed propagation, you definitely want to do P1. The other thing, but mathematically, what it turns out is that if you have a case where if you're scattering is say 100 times or 30 times higher than absorption, you may be able to get away with not worrying about the second derivative. But if scattering is not as large, so remember, we typically have G's of 0.9, right? So this means that you want, mu sub s to be, for me, I would say you want mu sub s to be 100 times larger than mu sub a. But if you only need mu s to be larger than mu sub a, then you can get away with mu s prime or mu a being only about 10 times higher. So you can probably push P1 closer to the visible than you can the standard diffusion. Again, this is only irrelevant for time domain, right? Because in steady state, it doesn't matter, and you really need mu s prime to be greater than mu a. Does that address? Okay. Okay. I think Tin had a question. Yeah. Uh-oh.
This has been my curiosity question for a long time, because these analytical solutions or approximation more like, so it's super fast to calculate, but the assumption is homogeneous and semi-infinite.
Yes.
So I want to ask you, Scott, and everyone who probably is in this space, is there an analytical approximation for something that's not homogeneous and not semi-infinite, something like a multi-layer, I don't know, diffusion model? I think I read something about Keenly working on that at one point.
Many people did.
Okay, so there are.
Yeah. I mean, there's actually at one point in our labs, we would do multi-layer spatially resolved reflectance. And it's really interesting because very close to the source, you get a decay that's dominated by the properties of the top layer and as you go further out, the decay is related to the bottom layer. And I mean, they work fairly reasonably as long as the layer thicknesses are large, and I think I know a lot of our field has transformed to using lookup tables, right? Because you can run tons of Monte Carlo simulations specific to the geometry of your situation. You do it over a matrix of optical properties and you do table lookup, which is fine. Things like in time domain in the brain, they still use diffusion approximation quite a bit because doing that table lookup is a lot more difficult. So there's still a lot of domains in our field that, steady state, I think we've gone, a lot of the field has moved to table lookup. But there are still pockets of our community that are still reliant on these approximations. And so they're still quite useful. Like diffuse optical tomography, a lot of it is still done based on diffusion approximation as opposed to transport-based.
Yeah, so related to the last question, I understand that Kinle and Limer work with the standard diffusion approximation for layer media, right? So I don't know if you work with the delta P1 approximation.
We have not published on it in layered in delta P1. Yeah, I guess probably there's no funding to do that primarily. We could do that. I think we've done some of that, but we've kind of pursued very Monte Carlo approaches to do that because typically, at least in my lab, we're dealing with tissues where the layer thicknesses are very small and you really
Yeah,
need to go to
I
Monte
see.
Carlo. Yeah.
Yeah, I want to particularly
Yeah.
thank you because of the nice approach on an explanation on the delta P1
Yeah.
approximation,
Thank you.
because I've heard about that
Yes.
like a lot, but I never tried to
Yeah.
understand better. And I think it's a matter of, as Scott said, a tribal thing in my lab. It's like everybody uses the
So,
diffusion
yeah, it's
approximation.
true.
So close to the end, you showed some examples for the different source types, like
Yes.
the extended source and then the Gaussian beam. And you also mentioned before that, like the perfectly collimated beam, right? But do you have examples of that to see how?
Well, I guess in some sense, no, I don't. The quick answer to your question is no.
Okay.
The more nuanced answer to this question is the fact that delta P1 still doesn't do that great when you have a very narrow beam, because and you can kind of see that from the Gaussian results, because the Gaussian results you see that that for smaller beam diameters you start to see a breakdown.
Yeah.
This is in low scattering medium.
Yeah.
In high scattering medium, it may work well, but even here, this is for a beam that's a full transport mean free path in radius. So that's still a 2 millimeter beam.
Yeah, I
fairly
see.
large. I imagine if you go to something like a tenth of a transport mean free path, it's not going to do so great. It's a hard problem.
Yeah.
Yeah.
And in comparison, the standard diffusion
Will be
approximation.
really a disaster.
Sorry?
Will be really a disaster.
Okay.
Yeah.
Thank you.
Yeah. You're welcome. Other questions? Okay, let's take a break. Thank you, guys. So who was it who wanted